So this time around what we're going to go ahead and do is solve for a much more complex example for spectroscopy. So what you're expected to be able to analyze is these four different versions of spectroscopy. And I would recommend that you approach them in this relative order. So start with the IR, then move to the mass spec, then the carbon NMR, then HNMR. And the reason being is just kind of a level of difficulty, if you will. So if you kind of work your way down, hopefully you won't get quite as frustrated, and you might find pieces along the way that can help you simplify your analysis when you get to the HNMR. What you're expected to be able to do at each of these steps is identify certain characteristics. So within the IR, we look for characteristic bonds, and from that we might be able to make functional groups. For the mass spec, we expect to find the molar mass, and then identify if bromine, chlorine, iodine, or an odd number of nitrogens are present. And then perhaps, if we want to push further, which we will in this video, find a formula and the degrees of unsaturation. We can then move into the carbon NMR, which is actually probably a little bit easier than the mass spec. We want to identify the number of unique carbons and their rough local environment. You could potentially get a little bit more out of carbon NMR, particularly if you use different carbon techniques, but that's all I expect you to get. And then in the HNMR, this is kind of the bread and butter, where you expect to find everything, including the kitchen sink, so we've got to be a little bit more careful with it. You've got the number of unique hydrogens, your local environment, the ratio of hydrogens, and your neighboring hydrogens. So a lot of information in there. And that, again, is organized in sequence from easiest to most difficult. Once we have all of these individual kind of characteristics from each of these versions of spectroscopy, then we can go ahead and put the structure together. Please try and go through each and every single one. Realize that when you get tested on this, I'm going to test some on the complete structure, but a lot of the points is going to be located in analyzing each of the individual spectra. So go through, analyze what you can, get that information down, force me to do some grading. Okay? So, the next part of this is we're going to use this table to go through and solve things, or this organization. I think the hardest part for starting out is trying to get all of your thoughts and pieces organized into a way that you can actually logically make sense of. So that's what this page is going to do. If you check your Canvas site, it's in a file called, I believe it's spec.org.pdf. Spec.org for organization. If you're watching this from the class, I expect 2 spectra to be solved using this. Okay, so this is for the lab class. 2 spectra should be completely solved using this information or this formatting to organize your data. I would highly recommend that you solve all of them using this, but some people are able to do the organization on their own. That's fine by me. You can finish off the rest of them however you see fit. But minimally, 2 spectra must be solved using this, or 2 structures must be solved using this format. So, into the nitty-gritty of this, we're going to start going through and processing these things and seeing what I see and see what you see. So I'll give you a second here. Feel free to go ahead and pause and identify what stuff you see, and then I will follow through. Okay, hopefully you've had a second to take a look and come up with your interpretations. I'm not going to lie, this spectra is a bit misleading. So in my first kind of glances at this, I see the sequence of 2 peaks, which typically only shows up for NHs, and in particular, primary NHs. However, if we look at the chemical shift, that's really, really low for an amine. So while I may initially consider that as an amine, I would probably step away from that and say something else, something weird is going on there. The next part of that, I do notice that this is broad, which is typically characteristic for an OH. Again, that chemical shift is really, really low, or sorry, yeah, that wave number is really, really low. So again, I'm kind of perplexed by what's going on with that. So that really kind of leaves me saying that perhaps what I'm seeing out here is some CH-SP2 stretches. It doesn't look like a standard CH-SP2, so I gotta admit I'm kind of confused as to what's going on out there, and that's fine. We just gotta label it. I do also see some peaks in here, which if we kind of roughly approximate, and I know my line is kind of awful, those are just under 3,000. Probably looking at some CH-SP3s. As we shift further along, I see this nice big broad peak, and again my first assumption from that, carbonyl, carbon-oxygen double bond. Then again, look to that chemical shift. I mean, we're looking at 1590. If anything, that kind of smacks of a carbon-carbon double bond, but carbon-carbon double bonds don't give us that kind of nice, characteristic, strong, intense peak. So it's again a bit odd, but I mean, that's what it is. Other than that, I don't see anything particularly exciting. This peak looks a bit interesting, particularly because it's coming greater than the carbonyl. That's sitting, oh, maybe 1700. Kind of hard to tell exactly, but it looks like about 1700, which could be a carbonyl, but again, the intensity way, way, way off. Okay? So with this IR, you notice I've got a lot of question marks. Okay, so it's not particularly helpful, but that's fine. That is what it is. So what we would do is go back to that chart or that sheet, and I'd write down the information that I kind of see there. You notice that I put a question mark next to the carbonyl, or carbon-oxygen structure, and the OH. I didn't include the NH, but I mean, we could go ahead and add that in here as well as a big old question mark. Kind of a bit obnoxious to spend all that time, what was that, a couple minutes, and get really nothing out of it. But, I mean, sometimes it's the way it works. Alright? So, now we can move on to the mass spec. Within mass spec, actually I guess before we do that, take a look at your chart and see what things we need to pick up. What we're going to be looking for is the M plus peak. We'll look for an M plus 2, see if that's there, come to any conclusions based on just our superficial interpretation, and then I'm going to go through and look at degrees of unsaturation and a possible formula, and then I provided some space here for some work. I'll admit that where I'm going to show the work is actually on the spectrum, and then we can transfer our information across. Okay, so taking a look at the mass spec. Those of you that may have seen these kind of spectra before might notice that this is an abbreviated spectrum, meaning that you typically don't see these spectra kind of die like this. You almost always see it come out square. Sometimes you'll get weird results. This compound happens to give weird results, so being a relatively nice instructor, I deleted those weird results from our interpretation. Okay, so realize that when I give you something, I'm trying to give you something a little bit cleaner, easier to work with. Okay, so now what we're going to go ahead and do is interpret. Our M plus peak is our peak furthest to the right. Okay, and then the tallest peak within 3 units. Well, we don't really have many options in that case. So let's count this out. So it looks like we've got a scale of 10, 20, 30, nope, how did they mark this out? Geez, that's pretty awful. Let me pause here for a second so I can think about it. Sorry, I just had to figure out exactly how they marked these. They've got these marked very, very oddly on this spectrum. We got 25 here and then 12.5, so they went up by fractions. Bit silly, but that's the way it works. Which means what we're looking at on, let's make sure that this holds consistent. Sorry about that, should have looked a little bit closer at the scaling. They abbreviated the front end of this too. We're starting at 40, 30, 20. So each of these markings is by units of 10. So if we go up to our peak furthest to the right, look really carefully, got a little little guy right there. So 110, what we're looking at is a signal about 111. Okay, which for sure you're going to be like, what the heck? Where do you get that from? Well, be aware that I will be nice, and I will give you that data so that you don't have to look down at that tiny little range and try and figure out what the heck is going on down there. So when you see it on the test, both on your final and any test that I give you, I'll tell you what that mass is. It'll be obvious, or it'll be given to you. So in this case, it's 111. We won't worry about this big tall peak. We'll talk about that at the end of the video if I feel there's time, and we'll just kind of move on from there. So 111 gives us our M plus peak. The next thing that we want to do is look for an M plus 2. Well, do you see an M plus 2? Okay, M plus 2 means we take, and I know it's kind of weird, so it's the M plus peak plus 2 units. So do we see a peak at 113? So we got a question mark there. Could argue, potentially we do, but for it to be useful for us, what we're looking for is its peak intensity to be either the same as our M plus or 1/3 the height. And it's certainly not doing that, which means no bromine and no chlorine. Okay, we could also say no iodine because the mass is too small. The next part of this, what's special about, so if we can try and section some of this off, what's special about our M plus peak happens to be an odd number. Our odd number means we have an odd number of nitrogens. Okay, so that is now guaranteed. For those of you that remember the IR discussion, that could very well mean that what we had back there was an NH or an NH bond showing up in our IR. So this is about where I would expect you to end. For those that are adventurous enough, we can go through and propagate this information out into a little bit more detail. So what we would do now is push this into a molecular formula. So within this, we know that the molecular weight is 111. Okay? And we know we have an odd number of nitrogens. So that could be 1, 3, 5, etc. We're dealing with relatively small organic molecules. It makes sense that we're probably only looking at 1 nitrogen. So we can subtract the weight of a nitrogen. When we do that subtraction, we end up with the mass of 97. Okay? Again, this is organic chemistry, so we can do some more simplifications. So this is minus 14 for our nitrogen. We can go through and say that the rest of that weight is going to be carbons and hydrogens. So we can divide by the mass of carbon, and we end up with 8.08. That means for a potential formula, we have the formula C8 with 1 nitrogen. And if we do the math out, we find out we'd have 1 hydrogen. Well, the odds of having only 1 hydrogen are pretty slim, so a more likely formula would be to use, instead of 8 carbons, let's use 7 carbons, but we have to account for that mass, so that's going to be 12 hydrogens to replace it, so we'd have H13 because we added the 1 hydrogen that was already in our formula. And what we now have is a potential formula. Okay, and we can now use that, summarize all this information back on our chart. But before we move back to our chart, if you remember back to our IR, we said we potentially had an alcohol, we potentially had a carbonyl, weren't really sure, but in either case, it sounds like there's an oxygen there. So while this formula has the potential to work, it doesn't take into consideration that we might have an oxygen. So as a kind of preemptive strike, what we're going to do is repeat this calculation, except this time instead of just subtracting the mass of the nitrogen, we're going to subtract the mass of the oxygen. So the mass minus our nitrogen was 97, minus our mass for oxygen, 16, gives us 81. Okay, same idea as we did before. We can now take our 81 divided by the mass of our carbons. Gives us, oh goody, I didn't write it out very neatly for myself. 6 point something, presumably. 6 point something. I don't remember. Apparently I didn't write the number down. Regardless, we get C6. If we count out our mass, we'll notice that we'll have 9 hydrogens, 1 oxygen. Sorry, again, nitpicky with the order, which eventually we'll talk about. And apparently color. And what we have now is a potential formula. We could try and go through and subtract a carbon out of this and replace that with our hydrogens. Not the greatest idea because we'd have too many hydrogens for the structure. We wouldn't be able to actually hold that many. We could have more than 1 oxygen, so we could again go back in and crunch those numbers. I'm not a big fan of calculating out these formulas because you could propagate out 3 or 4 or 5 different formulas and it just doesn't make sense. What I want you to see is at least 2 so you get an idea on how we went through and did those calculations. So we would now go back to our chart and we'd summarize this information into it. So our molecular weight was 111. No M+2 peak, which meant for our conclusion, which I didn't include on here, that we didn't have, so we had no bromine, chlorine, or iodine. We did have that odd molecular weight, which means we have an odd number of nitrogens present. Oh shoot, I didn't show the degrees of unsaturation, so we'll look at that in just a second. From our possible formulas, we had 2 possible formulas to work with. To get the degrees of unsaturation, remember I posted in that last video that silly formula to go through and do that work. So for our first formula, our C7H13N, the way it would work is we take 2 times the number of carbons, which is 14, plus 2, plus the number of nitrogens, which is 1, minus the number of hydrogens in our formula, which in this case is 13, and we divide that all by 2. What we end up with in that case is 4 over 2. So for our first formula, we get a potential degree of unsaturation of 2. Okay. Remember those degrees of unsaturation would be pi bonds and or rings. So you can have a mix of all of these things, so you got to be careful. For the other one, can go again, kind of crunch through that work. I know it's a bit crowded on here. We start with 2 times the number of carbons. Well, we had 6 carbons times 2, so we got 12, plus 2, plus the number of nitrogens, which is again 1, minus the number of hydrogens, 9, all divided by 2. You'll notice that we don't count oxygens in our calculation, and that's just because of the balance of hydrogens. So oxygen ultimately, while it takes a spot, it doesn't really take a spot because you could put a hydrogen on the other side of it. The nitrogen we have to account for because when it takes a spot, it actually gives in 2 hydrogen spots. So we get an increase of 1 extra hydrogen per nitrogen. So that's why we have to account for it. When we do that math, we'll get 6 over 2, which gives us a degree of unsaturation of 3. So again, 3 degrees of unsaturation means we could have 3 pi bonds, 3 rings, a pi bond and 2 rings, 2 pi bonds and 1 ring. So we get all these possible different combinations out of it. So hopefully we're still following along. You'll notice we're 19 minutes into this and this is it being explained rather quickly. So realize that a complete solve will take a decent amount of time. The next part about this is moving into our carbon NMR. So you'll notice that our carbon NMR is equally simple in comparison to the IR and mass spec as far as information. So we want to look for the number of unique carbons and then the types of carbon that come out of it. So we can look at our carbon NMR spectrum. We know this is our carbon NMR because we can look at the chemical shift range, and we're going up to that 200. Even if we didn't go up to 200, we'd know it's our carbon NMR because our number would be greater than 14 or 15 if we were looking at the HNMR. So what I would expect to see, again, minimally on this, we've got 1, 2, 3, 4, 5, 6 peaks, which means 6, whoops, come on now, 6 unique carbons. The next part of this is trying to classify where those carbons are located, so something about their chemistry within that 0 to 50 range. So as far as understanding this, we're looking at our chemical shifts. So you can either have those ranges memorized that are listed in that Spec packet, or you'd have to keep referring to it. Eventually you will need to have them memorized. That 0 to 50 range are alkanes, which means we're just looking at singly bonded carbons. In that 100 to 150 range, so this is going to be interesting, we're kind of pushing the threshold both directions. We've got one peak a little bit under 100 and one peak very clearly over 150. In that general range is where we would see our alkenes, or sorry, our pi bonds, okay, which classifies both for our alkenes and our aromatics. Okay, so we know we're going to have some kind of double bond within this. Just kind of nice because that matches what our mass spec said. We had a degree of unsaturation. The very last signal that we see is sitting right about 200. Very, very characteristic for a carbonyl. Okay, kind of interesting. We've mentioned that that carbonyl was present already, but it gave us very odd characteristics in our IR. Okay, so that's all I would expect out of the carbon NMR. You'll notice that all of that information is included on there. It doesn't have to look neat, but the information needs to show up in some form or another. So if you prefer to not use the chart, this is what I would expect to see over the top of the spectra. Back to our chart. Excuse me. We'd add in our extra information. You'll notice that I specified that we've got these 6 unique carbons, and then specified how they broke down. So 3 alkanes, 2 alkenes, and you'll notice I put a question mark there. And I put the question mark just because I thought it was a bit odd that those signals showed up kind of on outside of that standard range. And then I've got 1 carbonyl. Okay, so we can start to process if we wanted a little bit of this, and we could immediately say that our C7H13N isn't going to work because we have a carbonyl. So we could also cross out the degree of secondary of unsaturation. This also suggests that we could eliminate the question mark, and we're really looking at a carbonyl for sure. We don't know anything necessarily about that OH, because it could still be there. If it was, we're going to have to do some funky, fancy footwork with our formula because we've only counted for 1 oxygen. Okay? So, we're now kind of progressing through this, not too bad. We can move into our HNMR. There's a lot of information going into the HNMR, and the reason these tables, or I recommend these tables, is ultimately just to organize your data and get it into some fashion that you can hopefully make sense of. It was a method that a student had initially brought to me after I had apparently taught him how to do it, and I didn't even realize that I discussed it in this fashion. But it worked really well for him, so I decided that we'll kind of keep this process going with it. So what we're going to try and do is convert everything within the table, or within our spectra, into this table. So we're looking at the chemical shift, the integration, and the multiplicity. So what we're going to do is evaluate each of those kind of independently and slowly add the information in. Once all of our information is into the table, then we'll go through and actually start to interpret it. Okay? So to begin with, we can look for both our number of signals and our chemical shifts. So all we're really concerned about is where do we see peaks. Okay? And we got to be a little bit careful with the term peaks. What we're looking for is where do we see a distinct group of signals or a group of peaks. So for sure, I've got one out on the periphery, and I've got one here, and then we've got 3 up here. So we've got 5 distinct signals within our spectrum, which means 5 unique hydrogens, and we can now convert that information across. So what I see is something maybe 1.9. I see a signal at 2, 2.2, 5, and 6.5. Okay. These numbers don't need to be exact because the chemical shift doesn't give us that much information. So we're really just trying to approximate, much like we did in the IR. So we go into our table, and you'll notice that I dropped those numbers in. So our chemical shift is now listed in there. Okay, hopefully you see that. I did forget to put the number of unique hydrogens, and it's going to continue to not be there. So 1, 2, 3, 4, 5. We're looking at 5 unique hydrogens. Okay, so back to our spectra. You'll notice a little bit more information has popped up here, and that's because of ease of interpretation at this point. Realize that when you look at these, you'll probably see all of this information smashed onto one spectra. So when we go through and look, our integration information is given to us, okay, around each of those signals. If for some reason the integration's not given, say on like the ACS final, becomes a little bit trickier to deal with, and what you would have to interpret is ultimately the intensity of each of those signals. You have to take that with a grain of salt, because what we're looking at with the integration is the area underneath the curve, and while that area over here at about 6.5, or that peak height looks very, very small, you'll notice that it has the exact same area as some of those taller peaks. Okay, and the reason being is the peak is wider. The wider the peak, the more area underneath the curve. I know everybody loves calculus, but that's what's happening here. So we have to be a little bit careful with interpretations based on peak heights. You can do it, but it's a little bit wishy-washy, which is why I'll provide you these numbers. Okay? So we can now take this integration information back to our table, drop the numbers in. Hopefully I put them in there in the appropriate fashion. I think I did. And again, we'll now move back to our spectra to get our multiplicity information, which is going to be arguably the trickiest. So I'm going to give you a second here to take a look at each of these signals and see how many peaks you see within each signals. When it comes to what I'll give you, it will be more obvious how many peaks are there. This just happens to be the digital system. Okay, so I'll stop talking here for a second. Okay, hopefully you've had a chance to go through and look and decide how many peaks you've got. So let's take a stab at the first easiest ones. There's 1 peak. Not bad. This guy, also 1 peak. Now we've got a little bit of a tricky situation on trying to interpret this. If you look really carefully, and I tried to blow this up as much as possible, we actually have 1, 2, 3 peaks for that first signal. For the next one, I'll switch up the color. 1, 2, again, 3 peaks for the second one. And for that last one, we've got 1, 2, 3, 4, 5 peaks. Yeah, I know, obvious, right? Take a look at your Spectra packet. Hopefully you've already started to scan through that. You'll notice that when it's less obvious, I've provided zoom-ins or blow-ups of that range much in this fashion, so that you can actually see and interpret what's happening with those peaks. Okay? One more quick note before we kind of skip off from this is that you'll notice that when we mark these, okay, remember everything is supposed to be symmetrical. You'll notice these aren't perfectly symmetrical. If we connect our red lines, they're angled that direction. Same deal with our purple lines. They're angled towards our right. Okay, seems a bit odd. What about that last one? Where is that angled? That's actually angled back towards the left. When signals split, it turns out that they will split towards each other. Sometimes this is helpful, sometimes not. But what that means is that this blue signal sees both the red and the purple hydrogens. Okay? So the red and purple are neighbors of the blue, but not of each other. Kind of a little nuance of that information, but it's there, so we could take advantage of that. Can't stop coughing. So now we've got all of our stuff in here. We've got our 5 unique hydrogens, and we've got space to now go through and do the interpretations. So this is where it becomes interesting. So as we start off, I would pick any signal. Doesn't really matter which one to look at, but I'm going to start at the top, just in this case. I have a chemical shift at 1.8. What does that mean? So that's where my interpretation comes in. Okay. So that means we would have to go in and take a look at our chemical shift ranges, which hopefully you will or have already started to memorize. But even before you do that, there's a piece of information that's even more important that you could specify. There's hydrogen. Keep it simple. There's a hydrogen present if you've got a chemical shift. Okay? Based on that chemical shift range, we're looking at a hydrogen bound to carbon. Okay? There is no other information that we can pull out of the chemical shift. So don't try. Again, what we're trying to do is simplify this as much as possible, get it kind of neatly, concisely organized and put together. Okay. Next part of this, we would move to the integration. And we'll now drop in our interpretation on the integration. The integration says there's 2 hydrogens. Remember, it is a ratio, so it could be 4 or higher, so we have to watch out for that. But we'll start simplest first. What's the easiest way to get 2 hydrogens identical to each other? Hopefully, come up with the idea that we attach them to it. Alright, at this point you'll also notice that I'm going to start to add what I like to call hanging bonds. That means those bonds can't be hydrogen unless I've specified a hydrogen. Alright. Now we can move to our multiplicity. Our multiplicity says we have, or gives us some information about our neighbors. Okay, where our multiplicity is equal to the number of neighbors plus 1. So that tells us that our number of neighbors is 4. Okay, so we have 4 hydrogen neighbors. And this is where this can become a lot more interesting, okay, or more difficult to interpret. How do we get 4 hydrogen neighbors to those 2? We can't just attach a methyl group. So if we looked at a possibility here, I'm going to rotate it slightly. I can't just put a CH3 on there. We'll specify this as a different color. Because that CH3 is only 3 hydrogens and I need 4 neighbors. Well, let's just put on an extra hydrogen. Oh, that's right, we can't do that. Okay? So what this means is ultimately 2 possible conclusions out of this. The first one is that we run with those 3 hydrogens, and then on the other side we have another carbon with just 1 hydrogen. Again, I'll throw in the hanging bonds because those can't be hydrogens. So this structure works. This gives me a 2 hydrogen CH2 with 4 neighbors. Okay? But is that the only possibility? Okay, well, it turns out the other possibility we could go through and do, and this is where doing it in this chart is going to be difficult, because we don't have a whole lot of space. I could have just as easily split it up in this fashion. Okay, and again, hanging bonds. Well, which of these answers is correct? Because very clearly only one can be correct. Kind of up to you how you want to interpret this. I personally take a look at each of these and say, okay, well, what's the big difference? The big difference is that in one case I have a CH3. Okay? So if that interpretation is valid, then I should have a signal that integrates to 3 hydrogens. Okay? Because if my spectra is correct, it should be there. So what I can go through and do is now check my integration values. And what's the issue with my integrations? There are no integrations or signals that integrate to 3. This means that this structure cannot possibly be correct. Okay? That's a pretty big leap, but hopefully you can see how we went through and did that. So we draw out our 2 possible structures. Hopefully we only end up with 1, but sometimes we get multiple. And then we evaluate what we know about that structure or that piece that we've put together. And in this case, we know that it would have to have a 3 hydrogen signal, which doesn't show up in our spectra. This means that piece does not work, and I can now erase that. And I would transfer the other one in, but I don't want to draw it again. Okay, so our signal is that guy. Okay. Excuse me. Again, we can kind of run into an issue on how we want to interpret this. What I'm going to go ahead and do, because I think students seem to like this part a little bit better if we do it this way, is now summarize this piece. So down in our summary of pieces, I would go ahead and include that piece. Alright, so we now have that under our summary. We've identified a piece that we could now work with. Okay. Next part. Go back to the NMR. Okay, our next signal shows up at 2.0. So I'll go ahead and show that in red. Our very first interpretation, hydrogen. 2.0, probably a carbon. Get away with that, so I'll let that slide. If you're not comfortable with that assumption, then you can go through and put it as a question mark. The integration means that we have 2 hydrogens, so again, we are looking at a CH2. The multiplicity says 3, which means our neighbors must equal, whoops, I can count, sorry about that, let me try that again. Our neighbors must equal 2. What is the easiest way that we can get 2 hydrogen neighbors? Well, it's going to be easiest if we just go ahead and link it up with another CH2 out the other end. Right. We could again split it into 2 CHs. So our other option, which I'll draw in black here in just a second, would be that we had a CH, and I really didn't give myself any space on this. Carbon and then a CH. The issue with this particular piece is that, so we could go through that same logic that we went through and did before, we would have a 1 hydrogen signal versus 2 hydrogen signals. Well, we've got lots of integrations for 2 hydrogens, but we only have 1 signal for 1 hydrogen. That only having that 1 signal does eliminate this structure. Okay? And the reason being is because that structure doesn't have just 1 carbon hydrogen on its own, it has a second. So if that piece were valid, we would have to have 2 1 hydrogen signals. We don't. Okay, so that structure must be incorrect. Okay. We can again go through and summarize, put this down as a piece. You'll notice that I am not going to attach it to the previous structure because I don't know anything about that attachment. Okay, it's possible it's attached, it's possible it's not. So I'm not going to attach it. Now what we can go through is move back to our spectra. This time I'll go in black. So our 2.1, we have again a hydrogen. 2.1 is just starting to push the limits. That could actually be a hydrogen bound to some other atom. Since I'm personally going to say I'm a little bit questionable on that, I don't know. So it's going to be a hydrogen bound to question mark. We can then move to our interpretation. We have two hydrogens. So hydrogen, question mark, hydrogen. Just because we have two hydrogens doesn't mean it's a carbon, because it could very well be a nitrogen. Nitrogen can have 3 bonds, so we could have two hydrogens attached and still be able to continue our structure. It most certainly can't be oxygen, because oxygen would be done with that. We'd be at water. The next part of this is our multiplicity, which says we have two neighbors. That actually tells us a substantial portion of information. So the very first thing that it tells us, and I'm going to try and stagger this, is that we have carbon. It's not a question mark anymore. I'm going to try and zoom in. Whoops. We have a hydrogen bound to carbon, and we know that because if it was a nitrogen or oxygen, it would hide those hydrogens from other hydrogens, so we wouldn't have any neighbors. So at this point, we now know that that has to be a carbon. Okay. Again, two hydrogen neighbors, so we're running into the same situation that we had before, and we'll come to the exact same conclusion, that it has to be a CH2. Okay. We can't do two 1CHs. We could again go through and summarize our piece. You'll notice that we're starting to collect a lot of pieces that look really, really similar. We'll talk about that as soon as we finish our HNMR. Next piece of information, we have a signal at 4.9, which again means a hydrogen bound to a question mark. We have only one hydrogen, which really doesn't help us out much. And then we have a multiplicity of 1, which means no neighbors. So we're really left with pretty much nothing on that. We have no idea what that hydrogen is bound to at this point. That chemical shift falls in kind of a dangerous region. I would really avoid trying to interpret it. So we can now put in yet another piece, a hydrogen bound to our question mark. And then our very last signal, what color have I not used? Let's go with green. We're looking at a hydrogen again bound to a question mark with 2, so it's a hydrogen, 2 hydrogens to that question mark. Again, our our multiplicity tells us 0 neighbors. And we'd again put in that question mark. I can do one slight tweak from this. If you go back to the HNMR spectrum, what you'll notice is that that signal was very broad. Our peaks will become broader if the hydrogen can come on and off of the structure. So if it's attached to an electronegative atom, like oxygen or nitrogen. So what I can do with this is, instead of saying I'm looking at just a question mark, that really what I'm looking at is a hydrogen bound to a nitrogen. Okay, there's only one extra bond there, so we can write that out. Okay, and that's really only because that peak was really broad. The broader the peak, the more likely your hydrogen is attached to a heteroatom. Very, very rarely do we see a carbon or a hydrogen bound to a carbon come up with that kind of broad signal. It just doesn't happen. And we can again summarize our piece. I'm going to abbreviate it now as NH2. Okay, so we've got all of these pieces. So this is what our HNMR told us. The intent behind organizing it in this fashion is now, when we try and go through and interpret, we can now start to piece things together. Okay? And what do I mean by that? Well, let's organize everything we've got. So we can go back through the rest of our information. Our carbon NMR told it, our carbon NMR told us that we had a carbonyl. So in our summary of pieces, I need to add carbon-oxygen double bond. Okay, yes, this is getting really crowded, but hopefully you've got more paper. Okay. We have the potential for an alkene. Could throw in there, and that does not show up in our HNMR, at least currently, which makes this even more a bit puzzling. But we can't just throw in a double bond. We'd have to have some place to actually put it. when we go back to our mass spec told us that the formula we were working with was C6H9NO. Or we could go through and look at the molecular weight. Okay, either way, if we count this up, we got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Well, our formula, or even our molecular weight, are going to tell us that we've definitely exceeded the possible mass for this structure. That means there must be duplication within our structure. Okay? So with that information, what I would now do is go back to my structure and say, okay, where is something duplicated? Okay, hopefully you can see relatively quickly that we've got duplication with our CH2s. So what I'm going to do is erase one of those. Okay? So now I've got that kind of cleaned up. So if we now go back through and count, we've got 1, 2, 3, 4, 5, 6 carbons. Sounds good. 1 oxygen also sounds good. As far as our hydrogens go, we've got 2, 4, 6, 8, 10, 12, 13 hydrogens. Got another issue here. Our formula says only 9 hydrogens. 13 hydrogens is way too much. So what does that mean? Don't panic. Ultimately what it means, we are going to assume that we did everything correct so far and that we've got duplication again. Okay? So we now go back to our structure and say, okay, where did things duplicate? Okay? I see 2 sets of CH2s. Okay? But I don't necessarily know which one's which or how these things stacked out. Okay? So what I'm going to start to do is slowly start to overlay them. So what I'm going to do is call this our red hydrogens, our red structure. If we overlaid it, so our first one, so I'm going to call it red hydrogen and purple hydrogen now. If we called our red hydrogen over and just slid it on top, that would mean we'd have our purple CH2 out the other end. Right? If that's the case, our red hydrogen could be fine, set up as kind of a duplication, except that what's the issue with that? It now has 4 hydrogen neighbors. Okay? We only have one signal with 4 hydrogen neighbors, and if we look at our blue one, it also has 4 hydrogen neighbors. So that overlay didn't work. So what does that mean? Well, that means we should continue to overlay. Instead of putting our red hydrogen or our red carbon on that position, let's overlay it one further over. If we go through and do that, what's our result? Well, now we don't invalidate anything. Okay? What this means is that it's not just a duplication of our hydrogens, we actually duplicated our carbons as well. So what I can now do is again simplify my overall structures, and if I was writing this out in pencil I would then cross out my other one, but since I've got a digital pad I can erase this, and this now makes a little bit more sense, maybe. So let's go through and count it out. So we got 2, 4, 6, 8, 9 hydrogens. Perfect. Okay, so our hydrogens are accounted for. Nitrogen looks good, our oxygen looks good. Before we continue to play, let's recount and check our carbons. Carbons, we've got 1, 2, 3, 4. Crap. What the heck is going on with this? Now we're missing carbons. Okay, well, what do we know about those carbons? First and foremost, they cannot have hydrogen attached to them. Period. We don't have a choice in that matter. There is no hydrogen attached. Okay? And because we don't know much else, what I would go through and do is just add these 2 carbons as extra pieces. Okay? And as far as no hydrogens attached, there is one kind of exception to that. Notice we have a hydrogen with a question mark. Okay? That hydrogen can't connect to our nitrogen, because then our structure would end. It could potentially connect to our carbonyl, but then we would have seen an aldehyde stretch in our IR, and we didn't have that. And it can't connect, whoops, it's not the one I was aiming for. And it can't connect out to our other structure over here, because then our structure would end. That means that that hydrogen must be attached to one of those carbons. So again, what I'm going to do is simplify things. And in this simplification, I'm going to put on that hydrogen. Okay, and now I can erase my hydrogen with a question mark. Okay, I know this is a lot of stuff going on with this. Okay, so I now have 1, 2, 3, 4, 5, 6 carbons, 2, 4, 6, 8, 9 hydrogens, 1 nitrogen, 1 oxygen. Okay, so I now have those pieces put together. I haven't invalidated any rules within my HNMR, so far so good. Alkanes in my carbon NMR, I've got my alkanes, I've got my carbonyl, but I don't have that alkene. Okay? And the IR shows support for that too. Okay? We've got a potential CHsP2 showing up. And that means that this hydrogen that we just put onto our carbon needs to be attached to an sp2 carbon. Well, I only have one choice. Okay? There are 3 carbons with bonds or hanging bonds, but I need to somehow turn that carbon's 2 of those bonds into a double bond. There's really only one other atom that can hold that. That's going to be that other carbon. Okay? So we're looking at something along these lines. And again, notice the hanging bonds. Okay? Now it's a question of how can we possibly put these pieces together. Okay? And when we take a look at this, we're not going to have a whole lot of options as far as the organization of this goes. We'll have a couple, but not a whole lot. So let's go ahead and start to see what happens. So what we're going to do is slowly start connecting these things up. So let's pick my leftmost piece as my starting point. If I decide to attach the nitrogen to one end of that, that's a possibility. Okay, so we could go through and tag that on there. I'm going to need some space to draw. How am I going to do this? Well, we're just going to have to work with it. If we put that nitrogen on there, I get one extra hanging bond out the other end, which I could then hook up with either the carbonyl or the other piece. Okay, if I hook it up with the carbonyl, then I've got one extra bond, but my other piece has 3 bonds. That's a bit challenging. I can't fit anything else on there. Okay, and I know I've got all my pieces because I went through and looked at my molecular weight or my formula. So that selection didn't work. So we can't put the nitrogen attached to that carbon. So let's try something else. Let's attach the carbonyl. And what I'm going to do is go ahead and shift this structure a little bit. If we go ahead and attach the carbonyl to it, CH2, 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 and then we've got that hanging bond off our carbon. It didn't really actually matter which one I decided to attach, be it the carbon or the carbonyl. So that works. I can't possibly put the nitrogen on that end, or on the end of my 3 carbons, for the same reason that we encountered before. So what I'm going to go ahead and do is attach the alkene to it now. Okay, so I'm going to erase that little guy and attach it to the end of this. And I'd end up with my carbon, double bond, carbon, hanging bond, our hydrogen, and another hanging bond. And now it appears that we've got yet another issue here. Okay, what's that other issue? Well, within this structure I see 3 bonds, and I only see one more piece. That's a bit puzzling, to say the least. So before I get frustrated too much, I want to again go back to my data. And in my data, we'll notice that we did calculate a molecular formula, but we also looked at the degrees of unsaturation. And the degrees of unsaturation says that we have 3 degrees, which means I need either 3 double bonds, 3 rings, or some assortment of those 2. When we take a look at our structure, we only have 2 pi bonds, which means we're going to have to bring in another degree of unsaturation in some way. We could try and bring in another pi bond, but then that's going to change the characteristics, and we would have expected to see that show up in our IR, and that's not there. So instead of bringing in a pi bond, what we're going to go ahead and do is bring in a ring. Okay? So looking at how we could loop this together, we can either attach our carbonyl, or call it our blue hanging bond, to our red or to our purple carbon. Which one are we going to aim for? Well, let's count out the carbons in each of those. So if we went with blue to red, we would have 1, 2, 3, 4, 5 carbons. I guess I could have counted that out a little bit better. 4, 5 carbons. If we went blue to purple, we would have had 1, 2, 3, 4, 5, 6 carbons in our ring. Well, deciding between those 2 is a bit challenging. What we would hope or aim for is go for our lowest energy. Okay? Or the other option is just draw it and see which one works better or matches the spectra better. Okay? So now what I'm going to go ahead and do is erase that big long line, and I'm going to write it out as a structure again. Okay, so that we can look at those pieces. We've got either the 5-membered ring, which we might have to remind me here. With the carbonyl, hopefully like that, and then our hanging bond. Shoot, it's a good thing I erased that. I don't even remember now what my structure looked like. We had to have had... Oh my gosh. Okay, sorry. It's alright. Give me a sec. Magic of pause. I was able to draw it out so I could look at it. Draw it a little bit better. Carbonyl comes around, and we're looking at our double bond out to our hydrogen and the hanging bond. It actually turns out we're going to have a couple different ways we could do this. We could also go with our 6-membered ring along those lines. And I'm going to have to erase that nitrogen. And we could have gone this way. Between these, and we do still officially have another one for our 5-membered ring, but I'm going to eliminate the 5-membered ring in this case just because of the ring constriction. So what I mean by that is it makes sense to have a slightly more open ring and go with 6 carbons as opposed to a 5-carbon ring. As far as how you would approach that, it's going to be the same idea. We're trying to go with our best possible situation. So I'm going to eliminate the 5-membered ring from our discussion, and now it's going to be taking a look at these 2 structures. We would put our nitrogen on it in our last situation to attach that up. Now between these 2, do they both equally work? Okay. Well, it's really going to linchpin on our green hydrogen, which is either here or here. According to our NMR, our green hydrogen has no neighbors. So when we look 3 bonds away, we should not find a hydrogen. If we count it out with our leftmost structure, 1, 2, 3, that's an oxygen, or 3, that's a carbon, 1, 2, 3, that's a nitrogen, or 1, 2, 3, that's a carbon. So no neighbors. If we take a look at our other direction, 1, 2, 3, nitrogen, 1, 2, 3, carbon, 1, 2, 3, hydrogen. That means that leftmost structure cannot possibly work. So what we end up doing is looking at our two possible results and seeing which one invalidates our data. Okay, I know that was a tricky one, which means when we go back through our final structure, we could now rewrite out. We're looking at the NH2 with the double bond, carbonyl. And that is our final answer. You should be able to go through with that structure and verify that all of the data match. Okay? If we go all the way back to our IR, what was going on up here, okay, in that high range, is that we had a signal that looked like an NH. You know, nice two peaks there, relative, sort of broad, but we didn't get a very high chemical shift. Well, why not? Okay, what happens when we put that nitrogen next to that double bond? Well, what can happen with the lone pair on that nitrogen? It can share electrons into the ring. What does that do to the electrons between the nitrogen and the hydrogen? It's ultimately going to weaken that bond, and it shifts to lower frequencies. So we've got a resonance effect to explain why the NH2 signal showed up much lower in the IR. Yeah, we could take a look again at our carbonyl. Okay, we said that that frequency was ridiculously low. Well, go back again to our structure here. What happens at the very end of that? We have a resonance structure that puts all of the electron density on the oxygen and no double bond between the oxygen and the carbon. Without that double bond, our frequency shifts lower and our carbonyl shows up at a much lower frequency. Okay, so we can explain those weird oddities in our IR once we have the structure. But until we have the structure, we're lost. Okay? We could go back and look at the mass spec. Within the mass spec, you might notice that big tall peak. This is the part that I said I was going to talk about again. This is known as the base peak. It's the peak that's set to a relative intensity of 100. It is the most stable piece within that structure. Okay, we could look at the difference between the base peak and our molecular ion peak, and what you'll see that difference is the matter of a carbon and an oxygen. Turns out we could eject from the molecule carbon monoxide. Carbon monoxide, being an exceptionally stable structure, breaks off on its own, and that explains why we see this shift, okay, or why we see that base peak showing up there. Okay, so what we're looking at is the fragmentation of the molecule. So it's finding the car tire, okay, after the fact. Within our carbon NMR, I don't have anything extra to add to this, unfortunately. It is what it is. We could go through and look at our structure and verify that we've got indeed exactly what it asked for. We have 6 completely unique and distinct carbons. We've got our carbonyl carbon. We have this guy, which is part of our double bond and extremely electron de-shielded. Okay, so that probably means that it is the one closest to our nitrogen. We've got our other double bond carbon, and then we've got our alkanes making up the rest. Okay, so there's all of those individual pieces. And then we could go back through and look at the HNMR, but I'm pretty sure you're sick of looking at HNMR. What we're trying to do is convert all of that information out of that spectra and into some hopefully organized and interpretable fashion. Okay, I believe that is everything. So what we just went through and did in an hour was solve one spectra. Okay, and that's using someone that in theory knows it fairly well. So what you should fully expect with hopefully the easier ones, is looking to spend at least an hour to 2 hours to solve these. Please budget your time wisely to go through and solve these. It will definitely help you out in the long run. Okay, and just in case, make sure that that is the last slide. Yep, it is. So, good night and good luck.